Hi, the section 4.2 link functions. So until here, the logit function is used for regression of binary outcomes. And the logit function is characterized as the inverse CDF of the T, the aptitude random variable in section 4.1. So this function has some advantages. That, for example, the inverse function has simple analytic form. So logit is logit of P is equal to the log of P over 1 minus P, but also the inverse function. Inverse logit function is equal to the e to the power x over 1 plus e to the power x. So both the functions are really the simple, and it's differentiable, and it's easy to deal with. And derivatives, yeah, it's easy. And also a good thing is the likelihood function is convex, so that we don't have to worry about convergence. So logistic regression is numerical, the method. So we don't have a guarantee that we can reach the global maximum of the likelihood function, but actually the function is convex, so we can approach to the true answer with the monotone increasing likelihood. Yeah, but still we can use other functions if they are more suitable for modeling. So just logistic function is a specific function, so it doesn't fit all the data. So sometimes a different so-called link function is better. And instead of logit function, then we have the several other function that are often used in the binary regression models. So first one is probit. So this is pretty common because this uses the normal CDF. So to be exact, the eta is the inverse, the standard normal, the CDF. So you can see that so standard normal CDF. So P ranges from 0 to 1 and just the standard normal. So normal CDF like this. So 1 and 0, and here P, and here is eta. Yeah, so it's known that the phi inverse, this doesn't have an analytic expression. So we have to say that the phi itself is the integral of the standard normal. So negative x squared over 2 and 1 over 2 and dx, and this is basically negative infinity to x. So this is phi of x. So we don't have any analytical form for the phi inverse of x. So computationally it's difficult, but it's more natural statistically because it's normal distribution. For example, the probit model have the multivariate version. So multivariate means the y is multivariate. So the y, usually we only have one variable y, but sometimes we have y1 and y2. So y1 is success for in some sense, and the y2 is another binary variable. So for example, you play the chess with some other person and you play also the backgammon with the same person, then probably your outcome are correlated each other, and maybe for most observations that's both 1 or both 0, but some exceptions. So in such a case, that we have to think about the multivariate distribution, And the normal distribution is good to extend to the multivariate case. So in general, except for normal distribution, the multivariate distribution is really hard to define. I mean, meaningful multivariate distribution is hard to define. And the second one is complementary log-log function. So that is eta is equal to log of negative log of 1 minus p. So you can see that still p is close to 0, then eta is, okay, so I would say that the p is close to 0, the eta becomes negative infinity. Because p is 0, that is log of 1 minus 0. So that is the log of a very small number, 0. Slightly negative, so negative 0. Then we have negative sign, so positive 0. Log of positive 0 is negative infinity, so eta is negative infinity. In the same way, that you can say that the p approaches to 1, then log of 0 approaches to negative infinity, negative sign, so positive infinity, then log of positive sign, so eta becomes positive infinity. So still the p ranges from 0 to 1, then eta ranges from negative infinity to positive infinity. So this is actually the asymmetric distribution. And the corresponding distribution is called Gumbel distribution. And the other one is coset distribution. This is basically the inverse of Cauchy distribution. So PDF is 1 over pi times the 1 over 1 plus x squared. Yeah, so this is very heavy-tailed distribution. So in terms of the heavy-tailness, the Cauchy distribution is heaviest. So the Cauchy probit and logit probit. And the tail is heavier. And the normal distribution, the tail is most light. And the logit in the middle. But rather it's closer to the probit model. So probit model, normal, so the tail part is e to the power negative x squared over 2. So e to the power x squared, so that becomes very small when x gets larger. And logit, basically the order is negative or e to the power negative x. So it's still exponentially fast, but it's slower than probit model. The tail probability that goes to 0 slower for logit model. The Cauchy is polynomial rate, so it's much slower. And the why we have these functions? Okay, so at first the different data have different shapes. So if you use, for example, the bin scatter plot, sometimes logit or maybe probit or Cauchy fits better. But generally speaking, the heavier tail, then more robust against outliers. So Cauchy, that is more robust. So that means if some extreme observations or outliers, then the Cauchy is more stable. But sometimes Cauchy is less efficient to estimate parameters. So this is the property of the Cauchy logit and the probit function, Cauchy logit probit function. Okay, so now example. So insecticide, the concentration and death. So the insecticide concentration is at 5 levels, 0, 1, 2, 3, 4. Then we have the number of observations. For concentration 0, actually the 28 out of 30 the survives and only 2 deaths. But for concentration 4, the only 3 arrives and the 27 dead. So the only 10% that survives. And we want to see what's the difference when we fit the logit and the probit and the quotient and the complementary log-log transformation in binary regression model. So this is the baseline we have done the many times. So this is the logit function. And we use just the GLM function to fit the data. And you can see the coefficient intercept is negative 2.3. The coefficient for concentration is 1.116, standard error 0.18, and the z-value is pretty large, so it's significantly positive. So higher concentration, the more animals die, insects dies. And you can see the null deviance, and this is actually only 4 degrees of freedom and 64. So we highly significantly we reject the null hypothesis that the concentration does not matter for death. Okay, so next one, the probit model. So the same function, but we can specify the link function as probit. So just the link function, the default is logit. So we didn't specify in the previous slide. And here we have intercept and the coefficient for concentration. So this comes lower, 0.68. So in the previous one, 1.16. But since link function is different, the meaning is slightly different. So logit model that we can interpret as the odds ratio, but here we use different CDF, so we cannot do that. But the standard deviation gets even smaller. So it's actually even more significant, the z value and the more smaller p value. And excuse me, the null deviance, they're almost the same. Yeah, and residual deviance, it's almost same, slightly smaller, and we cannot reject the null hypothesis that the perfect model is better than this model. So this model is probably sufficient. Concentration is sufficient to explain the death rate. And this is for the complementary log-log transformation. Estimate the similar to normal case standard deviation at almost the same level, z-value almost the same level. So it's similar. Residual deviance gets a little larger, so it's actually slightly worse than probit logit model. And the quotient distribution, quotient link function, again, that we just changed the link function. Estimate is actually large, but the interpretation is different. So quotient, yeah, we will see, but the quotient CDF is a little, less steep. So that's why estimate is larger, probably. And the standard deviation is pretty large. So z-value is smaller, still highly significant. And residual deviance, they're slightly worse than the probit logit, but still the 3 degrees of freedom. So expectation is 3 under null hypothesis. So we do not reject the null hypothesis that the perfect model is better. Sorry, the current model is better than perfect model. We do not reject the null hypothesis that the perfect model is better. So our model is good enough. So these are the comparison of 4 models. And yeah, the fitted value, we can calculate it. And the fitted value, if you get the coefficient, the beta naught and the beta 1, then we multiply this by 1 for intercept part and the x value, concentration value for this parameter, and take summation. So this is basically the x beta hat. So this is beta hat. Okay, so beta not hat and beta 1 hat. Then so we now calculate the fitted value for probit model. So we have used the inverse logit function to calculate probability, but here the probit model. So we use the p-norm function, and that is 8.42%, 0.0842. So fitted value is 0.0842. And another way to calculate is just use the fitted function. Also, we can use predict function. Then we get the probability for all 5 observations. The first observation, just it coincides with this calculation. Yep. And if we use the predict function, fitted function, the fitted function, then we can calculate the fitted value for all 4 models. And we can use the sapply function to calculate fitted value for these 4 models at once. And since concentration level is 0, 1, 2, 3, 4, that we just put the row name as 0, 1, 2, 3, 4. Then the column names that we specify these 4 different models. Then we have these 4 different probabilities. So it looks similar, but it has some slight difference. For example, this probability is larger than others, especially logit and probit. And this probability is larger than this, and much larger than this. So we have slight differences. And to see the difference in a figure that we generate these 4 curves. So this is the fitted line by 4 different models. And okay, so anyway, we fit the same data, so mostly the same curve, but the most distinctive difference is here. So tail part is different. So actually, the Cauchy is pretty different from others, and this is because of the heavy tailness. So it doesn't, approaches to 0 fast. So it's pretty slow. And probit and logit, actually the logit is still slower than probit. So you can see that around here, still the logit has smaller probability than probit model. So in terms of the the tail probability, so maybe the other side also, but this probability does not approaches to 0 or 1 first for Cauchy distribution. And the complementary log-log. So this is the asymmetric distribution. So skewed to the right. So if we make a figure, actually it looks like this. So this is the complementary log-log function. So it's a little harder to interpret, but in this case, actually the tail is pretty heavy for the left-hand side, but the right-hand side, the convergence is fastest. So these are differences. So if we have outliers, probably the Cauchy distribution is more stable than others. If no outliers, then often the logit or probit fits better. And actually, in our case, the probit fits probably the best, while the fit is not much different between logit, probit, and the complementary log-log.